this video, we're going to talk about how polarity and nonpolarity affects solubility. So solubility is a property of what you dissolve in. There's a general rule that like dissolves like. What this means is that polar things tend to dissolve in polar liquids, and nonpolar things tend to dissolve in nonpolar liquids. If you have water, well, water is OH2. It has significant positives on those hydrogens and significant negative on that oxygen. As a result, water is extremely polar. In fact, we tend to average it and just talk about the negative oxygen side and the positive hydrogen side. Water is one of the more polar molecules that you can make that's liquid, and that's part of why it's so critical to life. It's needed to cause so many of our polar-polar interactions. This is really good at dissolving things like ions. If I have an ion, well, water can surround it. That negative oxygen can be attracted to it. And so, quick drawings here. You'll get lots of water surrounding an ion and helps that ion dissolve. Now, if you're not ionic, if you're just polar, things like acetone, so CH3, well, you still have a dipole. Granted, it's not an H bond, but it's still a dipole, and so acetone dissolves pretty darn well in water. You get your oxygens, your hydrogens, and those hydrogens can be attracted to that negative charge on the oxygen. And the oxygen can to the carbon, though it tends to run into these other methyl groups a little bit. It's actually one of the nice part about acetone. It also tends to dissolve nonpolar things, because those methyls are a large enough nonpolar component on the bottom, where the ketone is a large enough polar component on the top that it tends to work in both environments. However, if you have something like hexane, well, hexane is all nonpolar. It really likes other nonpolar things. And so if you've got kind of gummy material or oil and stuff on your tools, generally you use hexane and the like to clean them off. It strips other oils and gas and oil or tar and things like that off of equipment. Water, however, doesn't go into oil. Think about your salad dressing if you ever have any oil and vinegar salad dressing. They make separate layers. Now, it's not that you can't try, but if you think about having a bunch of, just going to make circular water molecules here, and then some oil and some more water. Right. Well, if you've got water everywhere else, you've got a couple oil molecules. Those waters are really strongly attracted to each other. They interact really well, they're drawn to one another, but these waters in between the oil molecules, they don't have strong attractions to the oil. The water has those strong hydrogen bonds. Right, so it's got some serious partial negative and partial positive, and that does basically nothing with the oils. So anytime one of these water molecules manages to drift out and then starts having strong interactions with its neighbors, well, to drift back in, it would have to break those forces. You'd have to pull, like pulling magnets apart. You'd have to put in some work to pull them apart. The result is that it's easier for water to drift out and be attracted than to break its attractions and drift in. Slowly over time, what this means is that the waters, by randomly bouncing back and forth, drift out more often than they drift in, until eventually the water has left between your two droplets of oil, and your oil just pulls up near each other. So if you've ever shaken up your salad dressing and it gets broken into lots of little bubbles, why do they reconnect? Why do they reform two different layers? It's this difference in preference for polarity. Water, being superpolar, barely interacts with the oil, but the moment it runs into any other water, it tends to stay with that other water. And so the oil droplets will recoalesce into one big layer of oil, more because the water is excluding them. It pushes them away as it escapes until they bump into each other, and then the oil merges together. And so eventually you get all of your oil pushed into one layer because that's the minimum amount of water that can be interacting with the oil. Let's think about solubility then. Let's go methanol, ethanol, propanol, butanol, pentanol. Methanol is infinitely water soluble. So let's say water soluble, oil soluble. It doesn't tend to go into oil very well. So we'll say not necessarily 0, but pretty darn low. Ethanol, infinitely water soluble. You can get any amount of ethanol and water to mix together. They don't dissolve too well in oils, but you can get a little bit of it. There is some hydrocarbon chain. And then propanol. This also you can mix any amount into water. But by the time you get to butanol, a little bit, about 5%, which means 5 grams of butanol per 100 grams of water, more or less. By the time you're to pentanol, almost none. However, in the oil side, what we find is that it flips. We were water soluble when we were mostly an OH group with very little hydrocarbons, but as we added more and more hydrocarbons, as we went from 1 to 2 to 3 to 4, what we found is our water solubility got less and less. Less of our molecule could dissolve in water. Now, when we say soluble, important point, we mean reasonably soluble in the human scale. You can always get a couple molecules of something to dissolve, but whether or not you'll form separate layers, or whether the majority of it will go to one layer instead of spreading evenly between two, if say you have water and oil. The idea is, are you able to get lots of it to dissolve or not? And so methanol, ethanol, and propanol, yeah, they all freely dissolve in water. But pentanol basically does not. It will nicely form its own layer. It won't really dissolve in the water. However, it will nicely dissolve in hexane or something. What we've done is we've shifted the balance between polar and nonpolar. If we think about methanol here, it's sort of 1 carbon versus 1 OH group. Well, remember, hydrocarbons, the nonpolar contributions are weak. They don't do a lot on their own. So this molecule is mostly polar. That OH is just worth more. So we are mostly polar. But as we keep adding more carbons, 2 carbons to a single OH, 3 carbons to a single OH, and finally 4 carbons versus 1 OH, and 5 carbons versus 1 OH. What we found is that our balance changes. If we think about size, treat them like size, I have so big an OH contribution and very little from my carbons. But as I build up more carbons, proportionately, I'm getting more nonpolar attractions. And so as time keeps going, while my OH is the same, my nonpolar from carbon keeps getting bigger and bigger and bigger, and eventually that nonpolar from carbon starts to get bigger than my OH. It's a balancing game. What you are soluble in is based upon the balance of your polar and your nonpolar. And so let's look at that pentanol. We said it was largely not polar in water. If I have this molecule, pentan 1,5-diol. Well, again, I've got 5 carbons, but now I have 2 OHs. So this is 5 carbon, 2 OHs. Result is I get a bunch of polar and then another bunch of polar. And so where previously we had our nonpolar now exceeding our polar, by adding another OH group, our polar starts to exceed our nonpolar again. If anything, this looks more like 2.5 carbons to 1 OH. If you were to divide it by 2 and keep a ratio that looks like our earlier molecules. Well, 2.5 would be right here. That should be nicely soluble. And indeed, pentan 1,5-diol is nicely soluble in water. By increasing our polar component, we've shifted that balance. The ratio of carbon to polar OH has shifted back in favor of polar OH. This made it more soluble in water. And so the general rule is that as you add more nonpolar, you will favor dissolving in nonpolar. As you add more polar groups, you will favor dissolving in a polar solution, at least within reasonably sized molecules. When you start getting to extremely large biomolecules, this breaks down. We will see that with things like soap, where if you have sulfate detergents and then long hydrocarbons, this is neither polar nor nonpolar. It is both in different regions. So really big molecules, this kind of falls apart on. But for any reasonably sized organic molecule, this is how you can determine whether you think it should be more soluble in water or more soluble in oil. Now, determining how soluble, that's not something we will expect in this course. Instead, you will have comparisons. If you had propanol versus butanol, which would be more soluble in water? Take a sec, think about it. When we had it up above, it was propanol. Proportionately, it's 3 carbon to 1 OH versus 4 carbons to 1 OH. So just by comparing the two, we see that this is more nonpolar. Well, the more nonpolar thing should be less soluble in water, so this is more water soluble. In terms of our solubility, these are the type of questions you'll see this quarter. There will be comparison between 2 or 3 or 4 molecules where you'll have to figure out, well, how strong are the polar interactions, how strong are the nonpolar between them, which molecule has the greatest polar relative to its nonpolar.